Okay, welcome to our next lecture. This one's on linked lists. Now you see here on the outline, we're only going to go through these first three because we'll come back and visit the second half of this lecture where we talk about implementing linked lists with C++ classes later in the semester after we've talked about classes. So we're only going to do the first half of this set of notes. And we've talked about linked lists before for those of you who were in 1030 with me. It's something we've certainly done before. So what is a linked list? It's a sequence of items or nodes or objects where every item is linked to the next one. And typically we start out with a singly linked list. So we have a couple of external pieces of data, usually a head pointer and a tail pointer. You technically don't have to have the tail pointer, but it makes doing things like adding to the end and stuff a lot easier. So head pointer points to the beginning of the list, tail pointer points to the element that's currently at the end of the list. Each node consists of some data, and it doesn't really matter what that data is for purposes of defining and even creating, to some extent, a linked list. In other words, the technique of this data structure, the concept, is independent of what kind of data we're storing in a linked list. Think of it like a blob, and the part of the blob that has the data is user-defined. And the only thing we have to know is there's a blob part, and then there's a pointer to the next node. So the node has two parts, a pointer, which points to another blob of the same type, and then the data part, which is application dependent, if you will, and user defined in many cases. So the head tells us where to start, and the tail tells us where the end is, so that we can add on to the end, or at least know when we've reached the end. And you'll notice here in the figure, one of the real common things to do for the tail pointer is either to point to itself, or to be a null, in other words, not point anywhere, so I know I'm at the end of the list. Or in some cases, we will create a circular linked list where the tail will point back to the head. And in some cases, that's useful. So which of those methods you choose is partly personal preference, but also, especially when we talk about having the circular one, may depend on what your application does as well. So each item has a data part and a link. We talked about that before. And of course, at least for now, we'll implement that link as a pointer. We've certainly talked a lot about pointers by now. We can think of it as an object or an instance of a class. That's moving into the C++ realm, which we're not going to do right now. And the last item either doesn't point to anything, so it's null, which is denoted by that self loop, or like I said, it may be circular. We can also have doubly linked lists, which this slide deck doesn't talk about. In a doubly linked list, it just means there's two pointers. So if we looked at this example with John and Mary, etc. If we put another little box on the front of each of these nodes, if you will, and had a pointer, so like here at Mary, before the words Mary, we'd have another little box, and it would have an arrow pointing back to John. And then Dan would have one that pointed back to Mary, and Sue would have one that pointed back to Dan. And John would have one that pointed to null, would have that circular reference. The nice thing about doubly linked lists is you can move either direction in the list. So you can go backwards or forwards. So you could potentially start in the middle and move backwards or forwards if you knew something about the order in which things were. Or you could start at the end and move backwards. So if I knew the linked list was in alphabetical order, for example, and I knew the thing that I was looking for, sorry about that, was near the end of the alphabet, then I might want to start at the end because I'd likely find it quicker moving from the end than from the beginning. Whereas if I knew it started with an A, B, C, then I would probably start at the beginning because those are closer to the front of the alphabet. So let's say this linked list represents a waiting line, Walmart or somewhere. So these four people are in line from head to tail. And in this case, the data part is a string, their name, John, Mary, Dan, Sue. And then the pointers are representing the order that they are in line. And if somebody else got added to the line, they'd get added at the tail, in other words, after Sue. And when it's time to process the next person, check them out or whatever, they would come from the head pointer. So we'd remove an item from the head, and then Mary would become the head of the list, etc. So much like when we talked about queues earlier. So it could also be numbers. Notice the basic data structure doesn't change, just the type of data. So the pointers are still pointers to whatever the node type is. And of course that size is going to change depending on how big the node is. And in this case, the data is just an int as opposed to a string, which would potentially be bigger. So, and it could also be a structure, like in your homework. Okay. So it could be a set of characters, not necessarily in order, but it's non-redundant elements. Okay. So the essence of these three slides that say that the data part of the node could be anything that we need to represent and keep track of and put in a particular order, whatever that order may be. But the basic data structure itself, or the basic organizational structure, if you will, of a linked list doesn't change just because the content of the data changes. Okay? So here we have it sorted. So the values are in a sorted order, which makes it a little bit easier because we know once we get to a certain point, for example, if I'm looking for G, if I get to F and there's no G, I know I'm done. Okay, so I know that it's got to be after that, but I'm at the end of the list, so I know it's not there. Whereas if they weren't in any order, or let's say I got to, let's say C wasn't here, so I got to B, and then I got to D, and I skipped where C would be, and it's not there, so I can stop looking, because I know if it's ordered, I can stop looking. If it's not ordered, then C could be all the way to the end. So I would have to search the entire list. A linked list could represent the values in a polynomial. I know this is that scary math stuff again, but if we had a polynomial equation, you know, a0 plus a1 times x plus a2 times x squared, etc., the coefficients of the polynomials, we could represent those in a linked list so that we could create code to evaluate the polynomial or do some other kind of manipulation that you've learned about in college algebra or calculus or somewhere like that. Again, just like the basic data structure of it, the operations on a linked list are pretty much the same regardless of what the data is. We need to insert an item, and then we have some choices about where we're going to insert. Inserting at the head of the list is pretty easy. Inserting at the tail of the list is easy. And sometimes we want to insert in the middle, because if we have a sorted list and we're going to add something, we probably want to put it in the right place, so we have an insert in the middle. So we might have multiple versions of an insert. Specify, or one version that you specify where in the order you're going to put it. And then we need a delete. So with insert comes delete. And again, it could be at the beginning, at the end, or in the middle. So I need to do search and locate it, and then I can delete it. So that means I'm going to need some kind of a search. So we have a search operation. Now the search does not always lead to delete. Search could just lead to, I want to find the value. So search would return the position, and then delete would use search to find the position and then remove it. Where search by itself would allow me to find something in the list and access it, maybe change its contents or use its contents without necessarily deleting it. And then the last couple of operations, or functions if you will, are size, tell me how many things are currently in the list, and then an is empty to just quickly check and see if there's nothing in the list, in other words, if it's an empty list. So let's look pictorially at how this would occur. So if I want to insert a new data cell called A, first of all, I create one. So I might do that with dynamic memory allocation, like with malloc. And then if I want to, here's what my list looks like currently. If I'm going to insert A at the beginning, then when I'm done, my insertion would look like this. So basically what I have to do is I have to go to the head pointer where it points. I'm going to change the head pointer to point to the new A, but before I do that, I'm going to make A's pointer point to where the head pointer used to point, which is this green first data element. Notice I have to change anything about that element, because it only points to the next one down the line. So its link value equals the old head pointer. So the first thing I would do if I were doing this programmatically is I, of course, create the node, and put the data in it. Then I would make this pointer equal to the current value of the head pointer, and then I would make the head pointer equal to the pointer I got back from malloc, for this value A. And that's what's represented down here. Oops. I don't know why that keeps happening. There we go. So link value of the new item equals the old head pointer, and then the new head pointer equals the value of the new object. So that's inserting at the head. Inserting at the tail, similarly, I go find the tail. This one used to point to itself or be null. So I make that one now point to A, and then I update the tail pointer to point to the new value. Okay? And make this one's tail pointer, or this one's pointer, be a null. Okay? So make the new value a null, make the value of the old item equal to the new pointer, and move the tail pointer. So three steps there. If I want to insert in the middle, then the first thing I have to do is after I create the element, I have to find where I want it to go. So maybe if I'm going to insert in the third position, so I have to go to that position, which would be like right between these two nodes right here. Okay. And what I have to do is I have to make this one's next pointer now point to the new item, and then make the new item point to the one this one used to point to, or probably in the other order. I'd probably make this one point to the one this one used to point to, and then I can update this one to point to the new one. So you got to be careful about the order, otherwise you lose information, or you have to save it off in a temporary variable or something. Similarly, deleting at the head and deleting at the tail is fairly easy. This would be like removing something from the list, for example. So I go to if I'm deleting from the head, I go to the head pointer, and then all I have to do is change the head pointer to point to this new one, and now I've removed that one from the list. Of course, if they're dynamically allocated, I'd probably want to free it as well, so I get rid of it, or consume it and move it to somewhere else, or whatever it is I'm doing with it when I delete it. So you can think of this almost like a pop from a stack. At the tail, similarly, that one's pretty easy. I just have to go to the tail, or traverse the list to the one right before the tail, make it now be a null or point to itself, and then free up the space for this old one, and it is no longer there anymore. And if deleted in the middle, the one I want to delete, the one in front of it, I have to make it now point to the one that the one I'm deleting points to, and that's it. Then this one can be taken out. So I just have to redirect this one's pointer to not point to the one I'm taking out, but now to point to the one after the one that I'm taking out. And these are pretty easy. Size just means I have to scan through the list and have a count, and then update that. So I go from the head pointer to the tail pointer, and count how many nodes are there. I could also keep that after every insert and delete. In other words, every time I do an insert, I'd add one. Every time I delete one, then I don't have to go through the whole list to do a count. And of course, if the head pointer is null, meaning it doesn't point to a node at all, then isEmpty can return a true. That one's easy. So if the head pointer doesn't point to anything, it means I haven't put anything in the list yet, or I've deleted everything from the list. And so that's a simple function. Searching, this means I have to traverse the list. And the only disadvantage of a linked list is that you always have to start at the beginning, at least if it's a singly linked list. If it's doubly linked list, you can also start at the end. So I have to start at the beginning, search sequentially, starting from the head item and seeing, is this it? No. Then go to the next item. Is this it? No. And if I know the items are ordered, then I can terminate early once I've gone past the place where the value would normally be. If they're not ordered, then I have to go all the way to the tail before I can determine if the value is in the list. But then once I find it, I can return a pointer to that node and access it, edit it, whatever it is I'm intending to do as a result of doing the search. Okay. So this is where we're going to stop in this particular one, because the rest of this set of lecture notes goes into implementing an item as a class. So we did an implementation in 1030, if you want to go back and look at those notes, of a linked list as regular C code. And of course you can find literally hundreds of them on the internet if you want to look at a more detailed one. Or you can ask me in class later if you would like me to do one on the board, and we can take the time to do that. But the rest of this one talks about implementing it in C++ as a class, which we will do, and we will go through, but it'll be later in the semester after we have talked about classes. So this is the end of the second video lecture.